Hello Science Alliance, I am Lara. This is Theatre of Science. I'm actually trained to teach physics to A level. Now I stream free live lessons into the internet, so I do an all ages lesson and I do a Lego story show and I do this for people who fancy a little bit of IGCSE physics in their lives. I like this lesson. I was just saying it's about something called Brownian motion, and you don't need to know anything before or after to do this lesson. This is a lovely standalone one. What I'd like you to do first of all, an excruciatingly difficult activity if you're as fidgety as me. Can you have a bowl of cold water, like on a table or something, on a safe surface nearby, and a bowl of hot water? I just boiled a kettle. You don't actually have to have it be that hot. And what I want you to do is to, I mean, for science's sake, it should have be the same amount of water in each bowl. I'm not going to worry too much about that. But what I would like is for you to, once you've got that set up, to not move the bowls. I know. As soon as I say that, I want to go, oh, I'll just put that one over there, move that one there. Well, just once you've stop fiddling, okay? Just leave them there and we'll do something with them at the end. If you've got some food colouring and a teaspoon or a knife or whatever. Okay, right, come back this way. So, I stream lessons to people of all ages, right? Because you're home educators, probably, if you're watching this live. So for that reason, I sometimes change my language to sort of suit all ages. Quite often I talk about particles, because a particle is just like a blob of stuff. It's not a very scientific word. Particle is something that like a 5-year-old can understand and a 20-year-old can understand. We're just talking about like particles of pollen or particles of hydrogen or whatever. For this lesson, we need to be really precise with our language if you're going to get marks at IGCSE. So the first activity, some of you are going to find this really easy and some of you will find it hard. It doesn't really matter which group you're in, as long as we're all on the same page by the end. What I'd like you to do, please, I've got 5 things. I've made it that they're all the same size. They're definitely not to scale. Hydrogen, which is like a little positive ball with a negative ball kind of whizzing around the outside. A pollen grain, a piece of soot. I've put oxygen. It's actually 2 balls that I've called oxygen that are squished together. And water, which is 1 ball called oxygen and 2 balls called hydrogen, all smushed together. And underneath you've got the words particle, electron, atom, proton and molecule. Can you use as many of those? It's confusing because there's 5 things and 5 words, but you can use the words as much as you like, right? Use each word as many times as you like. Can you match the things to these words? How many of these words describe each of these things? Do you get me? Like a piece of soot. Is that an atom? Is it a molecule? Is it an electron? Is it a particle? Or what? And then when you've done that, which of them are microscopic? That's actually quite a tricksy question. I was pleased to see that the people on Facebook yesterday who were like, oh yeah, Lara, I know how to use the word proton and electron and molecule correctly, even if they were smashing through the first one because they already knew it because they've done research before. A lot of them were getting the second one wrong. So if you haven't got a clue about the first one, because this is like your first science lesson ever, you probably have heard of the word microscopic and you could be maybe thinking about, what does microscopic actually mean? Like if you were going to be really precise. Tell you what, I've got some hot water left in my kettle and I can feel that my throat is slightly sore. So I'm going to literally give you the amount of time it takes me to go downstairs, grab a mug and come back up here. Okay, that's all the time you've got. Remember, you can use as many of those words as you like. Okay, how have you got on? I'll go through it, don't spend too long on it. Because if you do know, you'll have finished. And if you don't know, it's quite a boring question, isn't it? Because you just don't know and you want me to tell you. Here we go then. So, a lot of you will know about atoms. It doesn't matter at all if you don't, because we're going to talk about them a lot. We haven't even done the lesson where I teach you about what an atom is yet. We'll do that in radioactivity. But this is an atom. It's got a little positive ball called a proton in the middle. It's not a ball, but with this little negative kind of ball thing whizzing around the outside. Together, they make an atom. Like I say, we did it in electricity. We'll do it a lot more in radioactivity. But one proton with one electron whizzing around the outside, that is a hydrogen atom. If you add another proton and probably more electrons, then you end up with this, which is a helium atom. If you've got 3 protons in the middle and maybe 3 electrons whizzing around the outside, it's a lithium atom. So they can go up and up and up like that. If you've heard of the periodic table, it is a list of every atom that humans have ever discovered. So these numbers here, like 1 is hydrogen, 2 is helium, 3 is lithium, 4 is beryllium. Those numbers are how many protons each atom has got. We're not going to worry about electrons and protons today. We're just going to picture atoms as being little balls. So if you see just a circle with hydrogen written in it, that's a hydrogen atom, okay? So like the smallest bit of hydrogen that you can get, a hydrogen atom. Okay, so hydrogen is a proton and electron, which is an atom, so we'll just call it an atom. What about these ones then? Oxygen. So 2 oxygens smushed together, well, that's an oxygen atom and an oxygen atom that are bonded together. And over on the other side, you've got a hydrogen atom and an oxygen atom and another hydrogen atom, all bonded together. Don't say smushed in your exam, say bonded. They're both molecules. Particles that are made of more than one atom are called molecules. Particles that are made of more than one atom are called molecules. Even if it's 2 of the same atom, like oxygen, then that is an oxygen molecule. So actually you are breathing in molecules right now. The air around you that you're breathing in is, we talk about it as being oxygen, right? Oxygen really likes to come in pairs, so you're not breathing in individual oxygen atoms, you're breathing in oxygen molecules, 2 oxygens bonded together, and it's the same with the hydrogen that you're breathing in as well, that likes to come in molecules. So for every 100 air particles, should I flip you around? I feel like I haven't seen you for ages. Hello. Take a deep breath in, it's always good to do that, isn't it? I need to remember to do that. Force your body and your brain to slow down a bit. For every 100 air particles that you breathe in now, you're breathing in about 78 nitrogen molecules, 2 nitrogens bonded together, and 21 oxygen molecules, oxygen atoms bonded together, and there's 1 left. Do you know what the 1 is, like on average? This guy. 1 argon atom, just on its own, saying sorry, because it really messes stuff up. If you're doing an IGCSE exam, write molecules, right? Air molecules, don't say air atoms. There's only 1 argon, we can forget about him. Anyway, okay, so that's a molecule of oxygen, that's a molecule of water, and that's really the only way you can use those words. But what you can say of all of them, like I say, is you can say that they are all particles. So particle is a nice generic word, which just means kind of small bit of stuff. But if you are going to answer exam questions about Brownian motion, we're not really going to be able to say particles anymore, or we're going to have to be very specific about describing what the particles are like. Because of this reason, which of the above are microscopic? So you might have been tempted to say, like, I was really pleased in the comments yesterday, on Facebook when I did this yesterday, somebody said microscopic means you can't see it with your eye. That's not actually what microscopic means. Like, it's very close. You can't see it with your eye. But that's not what microscopic means. Lara, what are you talking about? It's good, isn't it? I know a lot of people don't like exams and think they're kind of pointless and silly. I sort of like how precise you have to get with exams. Microscopic, so it means it can only be seen with a microscope, which isn't quite the same thing, is it? A pollen grain can only be seen with a microscope. I know you might be thinking, you know, like if you've ever seen a load of lily flowers that have loads and loads of yellow pollen on them, can get on your clothes and stuff. You can see it, but that's loads of pollen grains all clumped together. Like in the same way that mould is like loads and loads and loads of tiny little fungus cells all together. But you can't see 1 grain of pollen with your eye, but you can see it with a microscope. And it's the same with soot. You can see loads of soot particles all bunched together on chimneys and stuff, but just 1 particle of soot, you can only see it with a microscope. You can't see it with your eye. So they are microscopic. Oh look, I've shown you a picture of some pollen. I forgot, under a microscope. Isn't that pretty? So the small spiky pink stuff is sunflower pollen. Morning glory is the big mint green one. Hollyhocks, love hollyhocks, are the big yellow ones. So this is all pollen seen through a microscope. Lilies are the little dark green ones, and castor beans are the very small ones. But this image is magnified by about 500 times. So the pollen here is all 500 times bigger than it actually would be. So you couldn't see it with your eyes. Thank you, Dartmouth Electron Microscope Facility, Dartmouth College and Wikipedia for that. Nice. But yeah, so a piece of soot is microscopic, but hydrogen and oxygen and water are not microscopic because you can't see them with your eyes, but you also can't see them with a microscope. You cannot look at oxygen molecules through a microscope. There's millions of atoms and molecules in one grain of pollen and soot. So that's an important difference which we're going to keep coming back to, and I'm going to keep testing you on today. All right, with the lesson's called Brownian motion. What does that mean? Well, here is botanist Robert Brown, back in the days when it was just like a law or something that everyone had to look incredibly miserable in photos. He was probably a super happy-go-lucky chap. But yeah, botanist Robert Brown in, I want to say, the late 1800s. He looks through a microscope and he observes something which no one else has ever recorded before. What he sees is pollen grains suspended in water. You okay with what suspended means? Like not floating on the top of the water, not sunk at the bottom of the water, just suspended. Like, I don't want to say floating, hovering, suspended, okay, in the water. And he sees them making this zigzag movement. I keep saying pattern. I keep saying making a zigzag pattern. I don't think that would be a good word to use because it suggests some sort of like logic to it. It's not, can a pattern be totally random? This was totally random. There's no way of predicting where these pollen particles, nearly said molecule, where these pollen particles are going to go. But they were moving in random zigzag patterns. He didn't know what this meant, but he called it, it got called Brownian motion. Okay, so I'm just going to pause here actually before we go any further. I've shown you on this PowerPoint a diagram of what was actually happening, okay? So what is actually happening to make these pollen particles move around is that what we would discover later is that all particles, like all atoms, everything in the whole big gorgeous universe is moving a little bit. Like even particles of ice, even though you might think ice particles are all like really rigidly bonded together because it's a solid and it's cold, actually those particles, they can't really move, but they're still vibrating on the spot. Air particles got absolutely loads of energy, they're whizzing around all over the place. Only if you cool stuff down, and we'll do this lesson a little bit later, if you could cool stuff down so that it had zero temperature, like zero energy, then it would stop moving. But we don't know of anything in the whole universe that does that. Everything has some energy. Even the coldest thing we found out there in the depths of space is still moving a tiny little bit. So the water particles were moving, and they were what the pollen grain was like bumping into, and they were making it knock around. Kind of like, I was going to say like a football in a ball pool, but if all the balls in the ball pool were kind of magically moving because they had energy. Anyway, here's your question, right? Robert Brown looked through a microscope and observed Brownian motion. This is a diagram of what was actually happening, but what did he see through his microscope? Can you sketch it? I'm just going to give you less in a minute, just to check how much you've understood of what we've talked about so far. So here you've got the little blue ones are water particles, right? Loads of teeny tiny little water particles all moving in random directions. Your big red pollen grain moving in this random zigzag, not pattern, movement, motion, I guess. Big red zigzag motion. Can you sort of, you can copy that diagram if you like, but tell me what you would actually have seen through his microscope. Hopefully you see what I'm getting at. I think this would be a good IGCSE physics question. It's not, as far as I know, but it would be a good one. What did he see through his microscope? you got it? If you've finished and you're bored, you can always like and subscribe, can't you? Or if you're watching live, you can go over to my Facebook page where I have put up a post saying, I'm live on YouTube. You can comment on this post. So if you've got a Facebook account, if you haven't, well done you, that's the right answer. Don't feed the evil corporate machine. But if you have got a Facebook account, you can go to my Facebook page, Theatre of Science Now, write a comment on the top post and I will read it out at the end. Have you done something like this? Oh, it took me ages that. Isn't that good? There you go. He didn't see the water particles. Is that okay? He saw the pollen through his microscope because pollen is microscopic, isn't it? You can see pollen through a microscope. He didn't see the water particles because, it seems a really weird thing to say, water particles are not microscopic. They cannot be seen through a microscope. So I rubbed it off because I realised it was a massive spoiler. But yeah, he saw the pollen grain moving randomly around in a zigzag pattern. He did not see the water particles. So he called, by the way, and this is why it's really good that I teach these lessons on Facebook first. When you're answering questions about this later, try not to make up words that are more descriptive than the words that I am using, okay? Later on, like on the Facebook lesson, when we started doing questions, I had people saying stuff like, water particles are nanoscopic. I haven't taught you that. I'm trying not to show my irritation. It's awesome that you're being creative, but if you're writing like an answer to an IGCSE physics question, that is not the time to start making up words. If you haven't heard the word, it's probably because you don't need it to get a mark in your exam. So don't say stuff like nanoscopic, just say couldn't be seen through the microscope, right? That's going to get you your mark. Where was I? Oh yeah, Brownian motion is the name for, let's be very careful here, Brownian motion is the name for this random zigzag motion that you observe when well, actually, no, this is the spoiler for the next question. Go on, you describe these particles for me, please, using the words that we've used today. How would you describe this red particle using some of the words that we looked at in the first activity? And how would you describe the blue particles? Oh, I should always bring the kettle upstairs with me. I'm loving just having this warm water on tap. It's very soothing. So you can use more than one word. Just, I mean, in exams, you don't usually get marked down for using more than one word as long as they're all correct. Like if the answer's big, you can't say, because it is big and small and medium size. But if you said like big, comma, colossal, comma, huge, you'd get the mark right. So how many words can you use to describe the blue thing and the red thing? Using words we've used today. Nanoscopic. You guys are adorable. There were loads of other words as well that I can't remember now. So I suppose at the very basic level, you might be saying water particles and pollen grain. Can you think of how to describe the pollen grain? There's a specific word that might well get you a mark. A little bit more detail that we've got about this, what we know about pollen. And even if you didn't know it, you know it because of the question I've asked you. All right, what I've put is water molecule. Remember, because they're molecules. It's H2O, isn't it? Two hydrogens and an oxygen bonded together. More than one atom. So it's a water molecule. And I've put microscopic pollen particle. It's not an atom of pollen, is it? Or a molecule, but it's lots and lots of like molecules and atoms all bonded together, but it's a particle, but it's microscopic because it can be seen through a microscope. Okay, right. So what Brownian motion is. I wish they hadn't called it Brownian motion, by the way. It's a lot of syllables to describe a very simple thing. It's just a microscopic thing which is moving in a suspension in like a random zigzag motion. Okay, that was quite complicated, wasn't it? A microscopic particle doing like random zigzag motion in a suspension, like suspended. So a pollen grain in water is a classic example, or a particle of soot moving in air, because air is not microscopic, right? You can't see air through a microscope. So if you looked at a soot particle, a microscopic soot particle through a microscope, you would see the soot moving in random zigzag patterns, but you wouldn't see the air. So it's very much the same thing. Brownian motion, just that makes me think of poo, because like brown and motion. But anyway, yeah, that is what Brownian motion is. It was the second most famous scientist on the planet who worked out what this actually meant, what Brownian motion meant. It depends whether you're probably thinking Newton or Einstein, right? If you live in the Western world like me. I thought Einstein came second to Newton, but anyway, Einstein wrote a very famous paper on Brownian motion in 1905. You don't need to know that, it's just interesting. At the time, a lot of scientists didn't agree that atoms even existed, but it turns out that they did. Well done, Einstein, and many others. Did loads more experiments, and eventually proved, sort of partly because of Brownian motion, they worked out that all stuff, like I say, is made out of tiny particles that are constantly moving about. I'm saying this all very quickly and just putting boring words on a PowerPoint. That is incredible, isn't it? What an incredible thing to know what pollen grain does when it's in water, and to use that and loads of other experiments to work out everything around us is made of teeny tiny little things, and they are moving all the time. Yeah, this is called the kinetic theory of matter. You might know if you saw my energy lessons, kinetic means moving. Right, I guess a little simple diagram on the board for you here, because it seems weird. Particles in a solid are all really rigidly bonded together, but they're still vibrating on the spot. They can't move around, but they're still vibrating on the spot. Liquids, you can sort of think of like particles in a ball pool. They're bonded together, but those bonds keep breaking. They can move around each other, so they've got more energy. And gas particles got loads of energy. They're very spread out. They're moving around all over the place. Okay, right. Pretty pleased with this. I'm pleased with this question because depending on like how much you've understood, you can get more marks. But hopefully some of you, all of you will see something in this. I've said, just the classic scenario that has never actually happened. An enthusiastic student, actually no, it happened a lot at school. An enthusiastic student has written a big paragraph about Brownian motion. And what I want you to do is to have a go at correcting where you think they've made mistakes. And hopefully I've been a bit sneaky and I've put in some mistakes that you won't find. If you want to be more positive, if you want to be a friendly marker, you could also tick all the bits that you agree with as well. So, an enthusiastic student has, if you've got my free printout from my website, I've put this on a big page for you so that you've got lots of room for writing. Underline all the mistakes you can find in this paragraph and have a go at correcting them, please. That's the important bit, not just crossing, but write what the correct answer is. And then tick the bits that you agree with as well. And then we'll do this activity with food colouring. Robert Brownian studied particles of pollen in water. So cross out anything you disagree with. You can improve it any way you like. There's a couple of places where it's not exactly wrong, but I think it can be improved. Robert Brownian studied particles of pollen in water. He noticed they moved in random zigzag patterns. Sometimes they moved in curved paths. It turns out this motion is caused by microscopic water atoms colliding with the pollen. What Robert saw proved once and for all that the particles in fluids move quickly and randomly. I'm going to draw my blinds down because it's got to the time of day where shadows are doing strange things. Clunk. There we go. It's darker, but it's less weird and flecky. I'm going to give you a bit of time because I reckon if you think that you've seen them all, you haven't. And don't forget that you can improve on stuff as well, even if it's not completely wrong. If you think there's a word missing that might get you a mark in an exam, by all means stick it in. Okay, so the first one isn't one that would get you a mark in an exam. In fact, I probably shouldn't even try and correct you on this because it might lose you a mark in the exam. His name wasn't Robert Brownian, it was Robert Brown. But, actually, you're better off remembering the word Brownian, aren't you? Because if you say that the random zigzag motion of pollen in water is called Brown motion, you definitely won't get a mark. But they won't ask you what the guy's name was, so anyway. It's Brownian motion, but his name was Robert Brown. Robert Brown studied particles of pollen in water. Is there anything wrong with that? Robert Brown studied particles of pollen. Yeah, they are particles, aren't they, of pollen? They're not like molecules of pollen. In water. Yeah. Can we improve that ever so slightly, though? What can we say about the particles of pollen? They were microscopic, so I'm going to stick the word microscopic in there. That's a better answer, isn't it, at IGCSE? Robert Brown studied microscopic particles of pollen. Do you know what? I haven't written suspended in water, but suspended in would have been a great little choice of word there. Okay. Robert Brownian studied microscopic particles of pollen in suspended in water. He noticed they moved in random zigzag patterns. I mean, I don't know if you'd get marked down for that, but let's not say patterns. Yeah, I just keep finding myself saying patterns. Let's say movements. Moved in random zigzag movements. It's not great English, is it? But it's probably better science. So that's okay as well, right? Sometimes they moved in curved paths. No, they did not move in curved paths. No, I haven't said anything about that. It doesn't make any sense, does it? If they're bumping into things and being thrown around, why would they move in curved paths? They move in straight lines. That's kind of what zigzag means, isn't it? It turns out this motion is caused by, microscopic water atoms colliding with the pollen. Okay, are you okay with the fact that water is not microscopic? Because you can't see water particles through a microscope. Is that all right? Water is not microscopic. You can't see it through a microscope. And water atoms isn't right either. You don't get an atom of water. You can't get a water particle, which is like protons with electrons whizzing around to the outside. Water is made of two different kinds of atom. So we're going to have to cross out atom and write molecule as well. Is that all right? Robert Brown studied microscopic particles of pollen suspended in water. He noticed they moved in random zigzag movements. It turns out this motion is caused by water molecules colliding with the pollen. Yeah, that's fine. What Robert saw, I didn't prove once and for all that the particles in fluids move quickly and randomly, but it helped to prove that the particles in fluids move quickly and randomly. You might have crossed out fluids and put like liquids. Yeah, it's all right. In physics, fluids are liquids and gases, actually, because they both sort of flow. And they do move quickly, and they definitely do move randomly. So, yeah, that's fine. Splendid. Right, well done, you lot, if you managed any of those. It's a good activity, isn't it? I feel like that's very good brain exercise. Kind of a fun puzzle. Right, let's do the activity. A lot of you will sort of know how this activity works. Don't move the bowls. Don't move the bowls. It doesn't matter if you have moved the bowls. It doesn't matter at all. It's just I shouldn't move the bowls because if I move the bowls and the water starts sloshing around, I can't prove to you that why I'm saying stuff has happened has actually happened. So I've got a bowl of cold water on the left and a bowl of hot water on the right. I've just got some food colouring on the end of my knife here. I'm going to jab the knife into each bowl and see what happens. If you've got this set up at home, you can do the same thing. What are we going to see happen and why? And is it Brownian motion? Oh, that's hard, isn't it? That is hard. What are we going to see and why? And is it Brownian motion? So if you've done this activity with me before, you might be able to answer the first one. You might even be able to answer the second one, but can you tell me, is it Brownian motion? Let's have a look. So that's the cold water. I should really put the knife in for the same amount of time, shouldn't I? I'll stab it in for 5 seconds. 1, 2, 3, 4, 5. There we go. Oh, so pretty. What's going on there? Beautiful. Okay, let's do it in the warm water. 1, 2, 3, 4, 5. What are you seeing? Did you think that the one in the warm water was going to spread out more than the one in the cold water? That's what's happened. Why? Why is the one in the warm water spread out more? So hopefully you're saying it's, admittedly, I haven't taught you this today particularly. Basically, the hotter that something is, the more energy it's got. So these particles of warm water, or should we say water molecules, have got a lot more energy. They're moving around a lot more than these water molecules that are cold. So there's more collisions. Collisions is always a good word to use. There are more collisions between the warm water particles and the food colouring than there are between the cold water particles and the food colouring. So that's what's causing it to spread out. Is it Brownian motion? Can you remember what specifically we said that Brownian motion is? You kind of, you know straight away in a way whether it's Brownian motion because we can see it. So Brownian motion is microscopic particles moving in a random zigzag pattern. Not pattern, is it? Moving in random zigzag movements because they're suspended. This is not technically Brownian motion, but it is being caused by Brownian motion. I know that's a bit awkward. Like, we can see it, so the food colouring is not microscopic. But if we could get down on a level, then if we could see the water particles, it is the fact that the water particles are constantly moving around in random directions that is making the food colouring diffuse through the water. So technically this is diffusion, stuff spreading out, not Brownian motion, which would be like one individual microscopic particle. But yeah, it's useful to know that, isn't it? You never know, they might test you on that. Right, you lot, that is the end of the IGCSE physics lesson about Brownian motion, except last week I was resting my voice, which was a very sensible thing to do. Thank you for bearing with me. But I put up a recording of a pressure lesson from like 2 years ago, but actually when I watched it back I was like, that's probably better than I would do this time. I was just going to reteach it, so I didn't. I just gave you the old recording. And I had a question in it, like one of the first times I've ever done this, where there was a question in it and I said, oh, I'll go through the answers to that next week. So now I have to go through the answer to this ridiculous question. It barely made any sense, I don't think. Exam questions are hard to write, and I did not do a good job of this question. But anyway, I will run you through it. First of all, I will just quickly say how you support me, like very quickly. You support me by chipping in towards my wages, by paying me £5 a month. That's how it works. There's this website called Coffee, which is for like people who do podcasts and stuff, people who do things for free if you want to pay them for the thing. You go to my About section on YouTube, or you go to my sign up button on my Facebook page. It takes you to this website called Coffee. You send me £5 a month, hopefully not too much for you, for like free IGCSE physics lessons from a qualified physics teacher who's got a first class science degree. But also, it all adds up to be a good wage for me. So thank you so much if you are paying my wages. That is the only way. Actually, anyone in my family makes money now, but it's working, you know? It's working. So thank you very much. I'll go over to my Facebook page in a sec. And so, yeah, link is in the description, actually. I think I've got better at doing that. The link to my Coffee page is in the description of this video. I'm doing that like it's down there. It's probably down there. Or it's in the About section on YouTube. Or if you're on my Facebook page, you can click sign up. Please, if you can afford £5 a month, send me £5 a month. It makes all the difference to my life. Right, here's the question. Don't worry if you don't understand this at all. This has got loads of different bits of science in it. Nice opportunity to revise some of the stuff that we've done in the past here if you're learning IGCSE physics with me. I said, trying to prove a point about pressure. Here is my niece's foot and here is my husband's foot, and I gave you how long their feet were and how wide their feet were, and I gave you their weights. Well, actually no, Peggy, pardon, I didn't. I gave you their masses. So, chums, the first thing you had to do was accept that you just had to be like, okay, so feet are rectangular now. We're going to work out the width and the length of the foot times them together, get that area, and we're going to say that's the foot. Yeah, sorry, obviously the feet aren't perfect rectangles, but let's pretend that they are. The other thing you had to spot was that mass and weight, not the same thing, are they? At this level, we say that mass is basically how much stuff is in a thing. So mass is like how many particles are in the body, if you like. My niece's mass is 12 kilograms. Whether my niece is on Mars or the moon or Jupiter or planet Earth, there's like 10 kilograms worth of stuff in her body. But weight is how much your mass is being pulled down. And that changes depending on where you are. So the weight on planet Earth, you get the mass and you times it by roughly 10, like 9.8 or 9.81. If you're on the moon, then it's a lot less. The moon doesn't pull on people as much as Earth does, which is why it's super fun to jump on the moon, I hear. So you had to change their mass into weight. Let's have a look. So I'm just going to put the answer on the board, right? For that first question, I said, which one will cause most pain if they step on my foot? So you had to work out the area of my husband's foot and my niece's foot. Then you had to work out their weight by doing their mass times gravitational field strength, which was 9.8 newtons per kilogram. Then, once you had their weight, which was how much force they were being pulled down with, and the area of their foot, you could use that to work out the pressure, and you should have got this answer here. So for my niece, the area of one of her feet was very roughly 0.0055 metres squared. My husband has a much bigger foot, 0.036 metres squared. And then if you work out their weights, my niece weighs a lot less than my husband, right? 120 newtons compared to 750 newtons. So you'd think, well, my husband weighs a lot more, so it'll hurt more if he steps on my foot. But no, because pressure is how much force is spread out over a certain area, true story, actually hurts more when my niece steps on my foot because she's got smaller feet. So actually it works out that she applied a pressure of 21,819 pascals compared to my husband's 20,833 pascals. So yeah, surprising, right? And then I asked, and I deeply regretted this question, how much pressure would my husband apply to the ground if he walked on the moon? Assume a spacesuit weighs 50 kilograms. And I didn't give you any more information, so I guess we also had to assume that his feet stayed the same size. Yeah, he's got one of those cool special spacesuits where you just sort of strap it on over your trainers, okay? So the answer was, well, this is the old equation, but now he's got more mass. He's got 50 kilograms more mass. So let's work out my husband's new mass. 75 kilograms plus 50 kilograms is 125 kilograms. But also he's got a new weight because he's on the moon. And the amount he's been pulled down on the moon is only 1.6 newtons per kilogram. So his new weight was mass times that, which is 200 newtons. So you've got 200 newtons of force being pulled downwards. He's still got the same shoe size. So the answer was 5,555.6. It's not 0.6, is it? I've done that rounding. Oh, no, I haven't. Yeah, 0.6 pascals. Phew. There you go. So well done if you attempted that. And deepest apologies if you didn't. That must have all been very boring and confusing for you. Well, maybe not. Maybe it gave you a little bit of revision, eh? Right, I'm going to quickly flip you around and go to my Facebook page and see if anyone has said hello to me. There are some people who are still lurking, so I'm assuming that you have. Surely. Would you have sat... No, I'm being rude about myself, shouldn't I? Perfectly interesting question. If you were learning already about pressure and weight and mass, then it was good revision for you. I'm not going to apologise. I spent a long time on that question and hopefully it brought you some useful stuff. Right. Stop shouting at like the made up people in my head that are complaining about me. And oh, here we go. Look, is that Edmund? It is. Woo. Oh, loads of comments actually. Splendid. Oh yes, Edmund didn't know what Brownian motion is. Taught Edmund the thing. And there's Bastian. Okay, I'm just clicking all comments. Edmund has never heard of Brownian motion before. Watching to find out what it is. Yay. Edmund thought that every particle listed was microscopic. Yeah, oh, because you can see individual molecules with an electron microscope, but you can't see water molecules, can you? Can you see water molecules under a microscope? Oh. Do you know what? I'm always like really pleased that Edmund's here and also a little bit upset about it. Yeah, so there are actual ways that you can see water molecules. But I'm just very quickly Googling it. Oh yeah, like you can use sort of X-rays as far as I can tell from an extremely quick Google, Edmund, I was like, actually, I haven't taught this lesson for a couple of years. Maybe technology has changed and I haven't noticed. As far as I can tell, you can't actually see them. Like, you could maybe make out their structure. We're just going to say no, you can't see them, okay? But make sure you check the exam specification before you, if you do an exam in like 3 years, then double check. Hello, Bastian. Oh, Laurie. Good afternoon, Laura. This actually fits in well with our science we did about, oh, no, you were learning about this yesterday. That's amazing. Fits in well with our science we did about this yesterday, and this will be a good recap. Laurie, delighted. I love it when it all fits together, eh? Hello, Freya and Hannah. That was really interesting. We'd also like to see brownies in motion. Yes, me too. Yes, very much so. All right, Kai. Oh, look at you lot all come in. Hello, Jacob and Todd the Blobfish. Todd the Blobfish is hard to say. Todd the Blobfish. Is this a toy? I want to see Todd. I want to see him. Hello, Casper. Hi from Casper. How do you be? I don't know how to respond to that. How do you be? One bees do good. Well. All right, Rocklin. Hello. Oh, Kai, what are you doing? We used the gravitational field strength of 9.8 newtons per kilogram and got slightly different values and thought your husband had 2 feet, but now realised he would be walking on 1 foot at a time. Yeah, again, exam questions are really hard to write, aren't they? In an exam, they would make it really obvious. Definitely, wouldn't they? Because you could easily be standing on someone's foot and have the other foot on the ground. You're quite right. And then you would have to, well, it would actually just be very confusing, wouldn't it? They wouldn't ask, they'd make it very clear. But yeah, you're right, it would make a different thing. The hot water molecules move faster than the cold water molecules. Nice. Casper as well, though, I was really trying, like, the hot water molecules, cold water molecules. Yeah, that is okay to say, isn't it? That's fine to say. I was trying to say, like, the water molecules that are hot, or the water molecules that have more energy, and the water molecules, because I didn't want people to think that, like, a hot water molecule was a different thing to a cold water molecule. But it is, because they're different. You know what I mean? Yeah, that's fine to say that. Oh, Rocklen, another great lesson. Oh, thank you. Going to teach Dad everything we have learned when he gets home. Excellent. Oh, that's nice. Ask him how he is first, won't you? Just in case he's absolutely shattered. See if there's any more comments, and then I'm gonna go. I think there might be, actually. Try it up. Oh yeah, okay, yeah, Casper's mum. You were also reading about brownie emotion yesterday. Look at you lot. May eat brownies tomorrow because it feels appropriate. It does feel appropriate. You're really making me want brownies. I think I might have to go and just make some. Oh, Rocklin! Talking of microscopic, these are spores from an uncommon fungi I found that a friend kindly looked at under his microscope for me to confirm the ID. Oh, that is cool. That is a lovely callback to other lessons that we've done. Oh, isn't that gorgeous? Oh, so he worked it out, or they worked it out from this, did they? I don't know what that is. Oh, definitely, you've got good friends. What's happening there? I love it, and the world is amazing. That's my conclusion from that. Hey, the world's amazing. Okay, you lot, right, I'm gonna go and rest my voice. And if you like my YouTube things, then I might see you tomorrow morning for when at 9 o'clock we're going to be making a little Viking ship, spoiler alert, and we're gonna label some bits of the ship. And at 10:30 I'm going to talk about nuts versus seeds. Okay, I will see you all very soon. Thank you so much for all your support. I'll see you soon. Bye.